All right, so waves also deals with energy because we've been talking a lot about energy with electric potential energy, gravitational potential energy, kinetic energy. There's lots of different energies out there. And what waves are all about is a wave is a transfer of energy in the form of a disturbance through a medium, typically. Not always, but typically. Types of mediums. Well, you're hearing me because air. My sound energy is traveling through air. You can also have energy travel through water. It's another familiar one, water waves. Or you can even have a spring. That's another form of energy where you're compressing a spring or even stretching a spring. They could going back and forth. But here's the key thing about waves is that some waves, let's get some smaller writing here. Some waves can be seen and some cannot. So water waves you can see, a spring you can see, but yet sound waves, you can't see those. Now, waves are caused by a vibrating source, and a repeating vibrating source can create two main waves. And again, you're hearing me with a sound wave, and that is my vocal cords vibrating, and so it's creating a sound. It's just creating a disturbance within the air. Now, we're going to talk more about sound waves tomorrow. But the two types of waves, the first one is a transverse waves. And that is when these vibrations occur perpendicular to the rest position. And so the one thing I'd like to use as an example, again, is a water wave, where you see the waves go up and down. Now, the rest position is a water wave. It's just nice and flat, right? Nice flat water lines. But then the waves move perpendicular, which means at a 90-degree angle to the rest position. And so these waves are going up and down, up and down. Compared to the rest position, they're at a 90-degree angle. Now, what we have is at the top of our wave is called a crest. That's terrible writing. I apologize for that. So I'm going to write a little bit better over here. So that's a crest. All right, that's the top of our waves. Where the bottom of our wave is called a trough. All right, now a couple other things to label is that from your rest position to the top of a crest, that's called your amplitude. Now, your amplitude, which we can use the letter A, is also, again, from your rest position down to the very bottom, is also your amplitude. Now, another big thing that we are going to be looking at is the distance between crests, which is called our wavelength. It's how long your wave is. Other things we have is spots where your wave hits your resting position. So right here's a spot. Right here is a spot. Let's see, our wave hits here at the resting position, and I guess I got another one here. These are called just nodes. So again, that is where your wave touches your resting position of the wave. All right, so I think that's about it. We got 1, 2, 3, 4. Yeah, we got our nodes in there. So there's again, this is what's called a transverse wave. And again, that's when the vibrations were moving up and down compared to the rest position. Now, another type of wave is called a longitudinal wave. And that's where the vibrations occur parallel to the rest position. So this would be, we can't see them, sound waves, or in fact like a slinky, where you're doing a pulse through the slinky. So you have spots where your wave bundles up, which are actually called compressions. So that's where your wave bundles up. And we also have spots where it stretches out. So those are compressions there where they bundle up. Spots where they, again, stretch out are called rarefactions. All right, so our wave moves in the same place as our direction. And again, here's a bundled up spot here where we have a compression. Now, just like the distance between two crests are the wavelength, the distance between two compressions is also your wavelength. All right, so there's a little terminology and just looking at two different types of waves. There's actually three types. We're only going to be worried about two of them. There's torsional waves, but we're not worried about that. All right, now a little something about waves. Given, for instance, a pendulum. Now, its rest position is just hanging straight down, right? But then you pull it back and let it go, and a pendulum goes back and forth. Now, when you're dealing with the waves, they're repeating themselves. And so what we say is that one cycle represents traveling from start to start. And so in the case of our pendulum here, you let it go, it swings all the way out to the right and then swings all the way back to the left. That would be considered one cycle. Now, a couple of things that we're going to be concerned about with waves is the frequency. And that's the number of cycles that a vibration can have per second. Again, our standard units there. And, using our standard units, and the units for frequency are hertz. Now, the period, T, is the amount of time that it takes for a vibration to complete a one cycle. And so in this case of the pendulum, you let it go and it swings all the way to the right and all the way back. Then you would hit the stopwatch, and that time would be considered your period. Now we have a couple of frequency or formulas relating period and frequency. And again, because frequency is the number of cycles that a vibration can have per second, well, frequency is equal to cycles, the amount of cycles this wave performs, per amount of time. And also, we have a relationship between frequency and period where F is just equal to 1 over the period. And the other thing is the same is true for the period, where we can find the period, how long it takes to complete one cycle, by taking 1 and dividing by the frequency. All right, so there's a 3 formulas for us today. We're going to have another one coming up, though. All right, so here we go for example of a pendulum, or a child swinging. So a child is swinging on a swing with a constant amplitude of 1.5 meters. What is the total distance that a child moves, after 3 cycles? So 3 cycles would be considered starting left, going back to the right, and then swinging all the way back. That would be 1 cycle for this kid. All right, again, where your starting position is the same as your end position. Now in this case, let's draw a little diagram here. We have our swing, and its rest position when you just leave a swing is straight down. And this swing is going to start outwards. All right, and I'll just put that little space there. That's the kid. Now we want to know the distance, and it has a constant amplitude of 1.5 meters. Now 1.5 meters is from your rest position to the very top or the outside of your swing. And then the kid is going to swing all the way out here to the right. And so the amplitude there is also 1.5 meters. And so what happens is the kid is going to travel for 1 cycle, 1.5 meters, then another 1.5 meters, but then he has to go back, he or she, I can't tell in this picture, So then it got to travel another 1.5 meters and another 1.5 meters. And so for one cycle, anybody on this swing is going to travel 1.5 meters, but you're going to have to do it 4 times. Which equals, let's see here, 1.5 times 4 is 6 meters. And so if we want to know how far the kid's going to travel in 3 cycles, well, we're going to take that number and multiply it by 3. So we get 3 times 6. Last time I looked, that equals 18 meters. And so again, because this kid, we get to be here, the swinging is an example of what type of wave? Well, again, the rest position is straight down, but in this case, our swing is going left and right. It's perpendicular. It's at a right angle to the rest position. And so this would be considered a transverse wave. Because again, a longitudinal wave, that would be like the kid would be on a spring. How's that? And like kind of a weird swing spring where they go up and down. Where did the 4 come from? In line 1. Here's where it came from. Is when I'm marking the distance that this kid travels. If they start here in green, they travel 1.5 meters there to go get to the rest position. Another 1.5 meters to get fully out to the right here. 3 times going 1.5 meters back to the rest position. And then a 4th time they'll travel 1.5 meters to get back to where they were. And then, of course, with any good swing, it just keeps on going. Hopefully that helped out. Let's see here. So that, again, would be a transverse wave. Now here's exactly what I was talking about here. So a mass is attached to the end of a spring and is pulled down. Afterwards, so this would be like a bungee cord. Afterwards, it vibrates 30 times in 24 seconds. All right, so again, this spring is going to be moving up and down. You can look at it again like a bungee cord. And so you're going to have compressions and stretches in this spring, or compressions and rarefactions, I guess they call them. But this the resting position is up and down, and the spring is going to move up and down. And so because of that spring moving up and down, that makes this a longitudinal type of wave. A little struggle spelling that word. Longitudinal. There we go. Good. Spell checks off. All right. So this would be a longitudinal type of wave. Again, because the resting position is up and down, and the spring is moving up and down. All right. But now back to the frequency. Okay. So I want the frequency. That's our F value. And the information I have here is it vibrates 30 times. So it goes up and down in 30 times. So that would be our number of cycles. Is 30. Our time is 24 seconds. And again, that's in our standard units. All right, so one of the formulas we looked at is that the frequency is equal to the number of cycles you can perform in 1 second, or cycles per time. Now in this case, again, we're going up and down 30 times. That's what it means by vibrating 30 times in 24 seconds. And so our frequency, let's see here, I got 30 divided by 24. It's going to be 1 point something is my opinion. Yeah, it is. And the frequency is 1.25. And again, you'll see that the units are hertz. There we go, or Hz. All right, then we get to B, where it says calculate the period of the spring's vibration. So that's that capital T. I'm not sure why they use capital T for the period. Usually they think they'd each, well, I guess a capital P is power, right? So, but we did have a formula again for the period, which is again just 1 divided by 1.25, the frequency. Let's put that in there first. 1 divided by the frequency. And so that I'm just going to take 1 and divide it by 1.25. And again, the frequency is going to be in our standard units because it's time, how long it takes for a vibration. And let's see, 1's smaller than 1.25, so we're going to get a decimal here. I get a 0. Yes, thank you, Joel. 0.8 seconds. So the frequency is telling us that there is 1.25 vibrations every second, but it only takes 0.8 seconds for one vibration. All right, so this is how many vibrations per second frequency, and period is how long it takes for one period or for one cycle. All right, so there again is an opportunity or an example of a longitudinal wave. Now, no matter what type of wave you got, oh, I think I got more, do I? Nope. Am I missing something? I am missing something. Haha. The universal wave equation. All right, so I'm going to have to draw one here. Let's see here. Add that. All right, so an example of a wave. Just give me a second here. All right, so we got a wave. And let's see, I'm going to draw a resting position in here of a line. There we go, there's our resting position. I'm going to draw our line in here. I'm going to do my best. Let's see here. Oh, up and down and up and down. There we go. So there's a wave for you. The best wave I got. And so again, the distance between our crests, so the tops of the waves, if you will, that is our wavelength. Now it's got a funny symbol, and that funny symbol is lambda. It's a Greek letter, and again, that is our wavelength. Now, here's the thing, is I want to look at how far this wave travels from dot to dot, from red dot to red dot, in the course of a wavelength. Now, an old formula that, well, you guys used before, and I've definitely used many times, is V is equal to D over T. Now, if it travels all the way from one top of the wave to one top of the wave, you've actually gone through one cycle because you've traveled this distance all the way down, back up, and all the way back up. So you're starting where you started, or you finish where you started, and then again it starts all over again. And so that wavelength is the distance we're traveling. But because we're just traveling one wavelength, the time it takes is actually, well, the time to complete one cycle. Which is called the period, which we just did. So I'm going to put that big capital T in here. All right, so we got a formula right now. So far, it's V equals our velocity of our wave is take the wavelength and divide it by the period. But I'm going to further change that up a little bit because I just want to make it easier because people don't like fractions. But our frequency is equal to 1 over T. And so instead of putting a T in the bottom, I'm going to put an F on the top for our formula. And so we have V, the velocity of our wave, is equal to F, I'm going to put in the top here, because it's equal to 1 over T, times our wavelength. And this is called, sounds really impressive, the universal wave equation. Which means universal, it works for every wave, whether it's a longitudinal wave or a transverse wave. It's our universal wave equation. The velocity of the wave is equal to frequency times our wavelength. All right, now let's try taking this equation for a little bit of a spin. All right, so it says example 1, the period of a sound wave. from a piano is very small. If the speed of the wave in air is 340 meters per second, what is the wavelength of sound? All right, so let's just see some of the stuff we got here. Again, I like to always write down. So the period of a sound wave is 0.0012 seconds. So that is our t. That is 0.0012 seconds. And let's get that in small print here. I'm going to need the room. All right, the other thing is we know the speed of the wave. So that's our v. And again, it's in our nice standard units there of meters per second. And what I want to know is the wavelength, which I don't have on my keyboard. That's a nice little funny symbol there. All right, so again, the universal wave equation is v is equal to f times lambda. Now, I want to know the lambda. I don't have the frequency, but I have the velocity. But again, with the period here, I can find the frequency because the frequency, again, is just equal to 1 over the period, which would be, 1 over a very small number of 0.0012. So 1 divided by a very, very small number. Let's see what I'm getting here. I pump that in, I get, big number, yeah. I'm getting 833.33. So now I've got my F. All right, so again, looking at that relationship between frequency and period. All right, so now I'm going to substitute my values in here. So let's see here. I got a V here of 340. My frequency is 833.33, again down to 2 decimals. And I'm trying to find my wavelength, lambda. All right, well, the only way to get lambda by itself here is I'm going to have to divide this 833.33 off. And what I do to one side here, I do to the other. So I'm going to divide the other side by 833.33. Those divide each other out, and all I got is our lambda here is equal to, let's see here, I got 340 divided by 833.33. Getting a small number, let's see here. I get, and again I get a decimal, 0.41 meters. Because again, it's got to be, everything comes in our standard units. Now here's something. It says, how far could the sound wave travel in 3 seconds? So there's a t there, 3 seconds. We want to know how far it can travel. There's our distance. Not sure, we want that. We got all this other information up here. So we got the wavelength, we got the velocity, the period, the frequency. We got a lot of stuff here. But you've got an old formula here, an old friend. V that I mentioned earlier today. Velocity is distance divided by time. And this actually is the velocity of air when it's a little warm out, about 20 degrees. I believe it's around 340, somewhere in there, but we'll get to that later on tomorrow, I believe. And so I know the velocity is 340 meters per second. All right, so let's see here. I got the V, I got the T, can find the D. All right, so I'm going to substitute in here. So we got 340 as our velocity. Our distance we're trying to figure out. And our time is 3. Now this is something I always, during math class, anytime I got something equaling a fraction, I like to create a fraction equaling a fraction. So I can cross multiply and all those fractions disappear for me. And so I end up with, let's see here, d times 1. Well, that's d. And then I got 3 times 340. Which is, I'm not sure here. Let's see, 1,000 and something. 3 times 340, we get, 1,020 meters. There we go. And this is actually how you can find out how far a lightning strike is. because you hear the sound of the thunder, and it travels at the speed of sound, which is roughly 340 meters per second, and you count the seconds. And that's how you can figure out how far the lightning strike was. Because lightning you see instantly, thunder you hear afterwards, because sound travels a lot slower than light, that's for sure. All right, what else we got here? I think we got one more example here. Bonnie and Clyde are fishing on Lake Ontario in separate boats 30 meters apart, sorry. When Bonnie is at the top of a wave, Clive is at the bottom of a wave, and they got a crest in between them. Now, if their boats bob up and down 20 times in 10 seconds, what is the velocity of the water waves? All right, so first thing I'm going to do here is I'm going to draw a picture of what's going on here. So, need my resting position. There we go. Oops, let's get rid of that. We've got some water waves here. So, let's see. So, who's on the top? Bonnie's at the top. Clyde's at the bottom. Okay, but they got a crest in between them. All right, so let's see here. So let's put a little boat here. There's Bonnie. Crest in between them. So there's one crest. There's two because they're at the top of the wave, and Clyde's at the bottom of the wave. So we'll draw his little boat in here. Okay. They are 30 meters apart. So I'm going to draw that in there. Okay, so that's 30 meters. Now, what else do we got here? If their boats bob up and down 20 times in 10 seconds. So that's telling us we're doing 20 cycles in 10 seconds. So that's our time. All right, and we want the velocity of this water wave. All right, so got a lot of information here, a lot of different things, but here's the first step. Is if I'm going to find my velocity, I'm going to use the universal wave equation. Now I could find the frequency with this information right here, because frequency is the amount of cycles per second. Per time, I should say. But it is the cycles per second. And so if I substitute in here 20 divided by 10, 20 cycles in 10 seconds, well, 20 divided by 10 is 2. And again, the units for frequency is hertz. So I've got the frequency, trying to find the velocity. Now I need the wavelength. Now, here's what we can look at here. There's a little bit of a relationship here over on my picture. Is from crest to crest. That's one wavelength. But we're going from crest to crest. We're not getting to the other crest. But we're getting to the trough, which is in fact halfway to the next crest. So I got 0.5 wavelengths. It's halfway there. And so this 30 meters is one length, and it's actually another half. And so, therefore, if you will, 30 meters is equal to, let's see, one wavelength plus another, so 1.5, or half another, I should say, of a wavelength. Because again, from a crest to the bottom, that's a half a wavelength, but crest to crest is a full wavelength. And so if I divide both sides here by 1.5, I'll finally get the wavelength, what it actually is. And if I take 30 and I divide it by, I think I know what the answer is here, 30 divided by 1.5, yeah, I get 20 meters. Which makes sense. So from crest to crest here is 20 meters, and then another halfway is 10. But that's all I need to now use my formula. And so now I've got the V, I can find the V because I have the frequency, I've got the wavelength, and so let's see here. Finally substitute in, make it a little bigger for a grand finale here. So our velocity is equal to, again, our frequency was 2 hertz, our wavelength here was 20, and so when we multiply those, well, 2 times 20 is 40, and again, the velocity, we're in our standard units for velocity, which is meters per second. So there's an example there. We got A lot going on there. I had to draw a diagram and figure out two parts to actually find our velocity.